So in this lecture, I'm going to extend what we learned about two-dimensional vectors in x and y to three-dimensional vectors in x, y, and z, or Cartesian coordinates. Here are the topics we're going to cover. We're going to talk about unit vectors, the length, direction, cosines, unit vector along an arbitrary direction, how we have an equivalent expression for cos squared plus sine squared equals 1 in 3D. We'll talk about horizontal and vertical angles, and then force along a line. So first we start with unit vectors, and when I'm writing them by hand, I'll put little hats like that for unit vectors I and j and x and y. So it makes sense that the unit vector for z would be the next letter k. So it's alphabetical. X, y, z have unit vectors I, j, k. And so here's x, and this is the unit vector I. Here's y, unit vector j. Here's the z direction, unit vector k. And they all have a length of 1, or unit. Next, I want to talk about the right-hand rule. Here are two different ways to do it. So the first thing is to make sure that you're using your right hand, not your left hand. Otherwise, you'll get it wrong. Unless I say use a left-handed coordinate system, which I would never do. So one way to do it is to point your fingers towards x in such a way that they can curl only towards the y. So in this case, this person has pointed their fingers towards x and curled their fingers in towards y, and then your thumb will be pointing in the z direction. So another way to do it is to make a gun with your hand with your thumb pointing in x and your index finger pointing to y, and then where your middle finger points out will be z. So whether you use this technique or this technique, make sure that you can do the right hand rule. And there's even a t-shirt you can get for the right hand rule right there. Right hand rule for the engineer. So the next topic is Pythagoras theorem. And so we all know that in 2D, r squared is x squared plus y squared. Well, in 3D, r squared is just x squared plus y squared plus z squared, which means that r is the square root of those three things. The next topic are direction cosines. Direction cosines are the cosines of the angles made from a 3D vector to the x, y, and z axes. So in this picture here, here's the vector. Let me highlight the vector in green. And the angle from this vector to the x-axis is a direction cosine in x. Is the direction angle in x, and the cosine of that angle is the direction cosine. The angle between this axis and y, the cosine of that angle is the direction cosine in y. And finally, the cosine of that angle is the direction cosine for z. And so all you really need to do is if you take v times the direction cosine in x, that will give you the x component. V times the direction cosine in y will give you the y component, and v times the direction cosine in z will give you the z component. And so here's just another picture of the angles alpha, beta, gamma between the vector of x, y, between the vector and x, y, and z. Excuse me. And so you take the cosines of alpha, beta, and gamma, and those are the direction cosines. So you know that cosine squared plus sine squared equals 1 in 2D. So we're asking in 3D, do we have a similar thing? So here's a triangle, and we know that cosine of alpha squared plus sine of alpha squared equals 1. But the sine of alpha is also the cosine of beta. So we have cosine alpha squared plus cosine beta squared equals 1. So in 3D, if you take the direction cosines, cos alpha squared plus cos beta squared plus cos gamma squared, that will all equal to 1. So this is the equivalent of cos squared plus sine squared equals 1 in 2D. In 3D, you just take the direction cosines, and those squared all add up to 1. So another way to do coordinates in 3D instead of x, y, and z are to use horizontal and vertical angles. So the horizontal angle measured from north is called azimuth, and the angle vertical from the horizon up to your object is either called altitude or elevation. And then of course you need to know the length of your vector to position a vector. So a quick note on this word azimuth. In the textbook, Hibbeler calls the angle downward from z, so vertical down to the line azimuth. But as we saw in the pictures above, astronomers call the horizontal angle azimuth. And so if you're taking surveying, it's also the horizontal angle. This reminds me of when I was at the University of Hawaii taking a surveying class. My surveying professor was Dr. Narendra Saxena. And one day we're out in the field and I was mimicking his accent, and I said, we must determine the azimuth. And I turned around, he was right there. I was just such a punk when I was a student. He was the nicest guy, and I have never forgotten after that that the azimuth is the horizontal angle. Dr. Saxena has since passed away, and he was really the best surveying professor ever. Okay, so now I want to talk about how to create a unit vector. So let's start off with something we know. We know that 5 divided by 5 is 1, right? Or if you have any variable r divided by r, that's 1. So if you take a vector r and divide it by the length of that vector, which is a scalar, the length will be 1, right? Like 5 divided by 5 is 1. So the length is 1, but you preserve the direction. And so if you want to get a unit vector in the direction of r, this is what you do. The unit vector in the direction of r is the vector r divided by the length of the vector r. We will use this over and over, so you need to understand this concept. For example, you will be asked to find the vector of a force with magnitude f along the direction of a vector r. So the magnitude is f, and the direction, the unit vector in the r direction is, remember, the vector r divided by the length of r. And so finally, we're going to talk about position vectors. So a position vector just goes from the origin to the vector. So here I have these coordinate axes I'm drawing. There's 0, 0. And so if that's point A, that vector there is RA. If that's point B, that vector there is RB. But sometimes we want to know the vector from A to B. Okay, so that's the vector from A to B. Okay, so you know that RA plus the vector RAB equals the vector RB, right? So all I did was took that vector head to tail, and that should all add up to this vector. So RA plus RAB equals RB. So solving that for RA to B, that's just RB minus RA. And I just remember this as you end at A and you end at B, you start at A. So if you want to go from A to B, you take the end minus the start. Like I ended 10 miles from here, I started 2 miles from here. 10 minus 2 is 8 miles. You do the same thing with vectors. And so that's how you get a position vector relative from A to B. This will become especially important next semester when you take dynamics.